Right. Testing 1, 2, 3. Right. So we good. So one section 10.6. Yes. On section 10.6, alternating series. So for alternating series, pretty much we need to have the term of -1 raised to something, and that will change the sign from positive and negative. Doesn't matter if this is to the k or to the k plus 1. This is the power of -1. We're alternating between positive and negative. Right. And so we check that term out. We have what's left is h of k. Of course, f k by itself is only positive term. Actually, or negative. It doesn't matter. Actually, yeah, actually, just that should be positive because we take the sign out. That should be positive. Right. And if that term is non-increasing, either decreasing or constant, of course, they will be equivalent. And then the n term goes to 0, or the h of k go to 0 as k go to infinity. In that case, if both of these are satisfied, then the series is convergent. And like I said, this is rather obvious usually when we see -1 to some power. That's what we use. So we did this example. 1, C, 3. And one example 3. Right. So if this example, obviously that is a -1 raised to a power. So this is alternating series. Right. And it doesn't matter where we start. Missing the first few terms still okay. So even we don't start from 0 or 1, it doesn't matter. What matters here is we have -1 to the k power. That is alternating series. So first, when we see this, that is the alternating series. Alright. So with that, we're going to take away that term, and what's left, we call that AK. So h of k is equal to ln of k over k. I did mention that k equal to 2 doesn't matter. However, we cannot. In this problem, it does. Let's take a look. Ln of 0 is undefined, so that's why it cannot be 0 here. And Ln of 1 is equal to 0, and that is not negative. I mean, that's not positive. So we put k starting from 2 to guarantee that Ln is positive. That's the only reason. All right. So after that, now for alternating series, there will be two things we need to watch out for. The first one is h of k non-decreasing. I mean non-increasing. Right. To do that, there are a lot of ways. If we show that as k increase, the whole thing decrease, then that's good. Right. Just quickly look at our list, the ranking, the functions. Ln is going to be less than polynomial. So certainly the top grows slower than the bottom. Because of that, the bottom grows a lot faster than the top. Then the whole thing will go to smaller and smaller. Because the top goes too fast, the whole thing will go to 0 essentially. And not only that, it goes to 0, it is non-increasing as well. But to actually definitely say that it is non-increasing, the best way is, of course, when we say that and let the function be equivalent to it, because Ln of x over x. So we have that instead. Our function is that of a sequence. Right. Now we take the derivative. Derivative of this using the quotient rule. Derivative of the top times the bottom minus the top with derivative of the bottom over bottom square. Derivative of Ln of x is 1 over x. Then times x. And then minus Ln of x. Derivative of x is 1. So what we have is 1 minus Ln of x over x squared. Right. Ln of 2 is negative. Ln of 3. Actually, let's just look at the function. Better yet, look at the function of y1 minus Ln of x. Right. So, actually, when x equal to 2, right here it is positive, but after that, it is negative throughout. So we say, because Ln of x going like that, so it's Ln of x is increasing, and then y equal to 1, And of course we see that ln of x is bigger than 1. So 1 minus ln of x is negative. I'll just say this one less than 0. Of course that for x bigger than 3. Because 1 is less than ln of x. Yeah. So that's one's negative. And if derivative is negative, that means it's decreasing. Of course, decreasing make it non-increasing. Right, so that check. And then the second box we need to check is what happened as the k goes to infinity. So we're going to put ln of x over x in here, or just ln of k over k. It doesn't really matter. For this, first thing we put in infinity. Ln of infinity, Ln will go to infinity. And that is indeterminate. So that means we can use the Harmonic rule. We should use x, but that's perfectly use k. Derivative of ln is the reciprocal function, so we have 1 over k, and derivative of k is 1. So divide by 1 is itself. So we just have that. And now put in infinity. 1 over infinity. A finite divided by infinity, that go to 0. Oh, by the way, is that equal to 0? And it does. So both of these conditions are satisfied. So the series is convergent. Right. So once again, for alternating series, we're going to have that term. We're going to have that -1 raised to some power. And then for alternating series, we need to check two things. Is the term not increasing, and is the term goes to 0 as we go to infinity. Right, both of them are satisfied, so it is convergent. And we'll go to the next part of the section. the remainder in alternating series. Right. So obviously the alternating series will go like this. Positive, negative, will just go up and down. Like that. And we said let the remainder for the n term is s minus s of n. So the difference between the series go indefinitely and the series stop at n. First n terms. Sorry, forgot the n. Alright. So that is less than or equal to the next term. Right. Let's look at this example. How many terms are needed to approximate the values of the series with a remainder less than 10 to negative 4. Right, and we have the series So the series go like that. So let's look at see how that works. Right. So math option 0. Let's use x instead. Equal to 1. For now, let's say 5. And we have fraction. Right. So we have that. And then and we just keep doing that. Right. So we getting closer. How about 101? So the number getting closer and closer. However, it's still out. I think switching between the numbers. I would demonstrate. We need one more. Right. So if because the series alternating one positive, one negative, so just adding something, subtract something, adding something, subtract something, so just go up and down, vibrate about a line. So you see negative 0.688, 698, and 688. So kind of up and down some values. The point here is that series So look like we have something like this, and we have, so that will change in the sign, and it will approach into a values. And the question here is how many of those terms do we need to make sure that the difference between the term changing is less than 10 to negative 4. So for alternating series, that's very easy to determine. It is r of n less than or equal to h of k plus 1. And this is h of k. So h of k doesn't including that. So first of all, in this case, we have h of k without that term. It's just 1 over k. For k plus 1, we have 1 over k plus 1. And if we want this to be less than 10 to negative 4, we just make it equal to 10 to negative 4. And then we just go ahead and solve for k. And 10 to negative 4 is 1 over 10 to the 4th power. And we solve for k, cross multiply. So k is equal to 10 to the 4th minus 1. So that is 9999. So if we want this is correct up to 4 decimal places, that means we're going to need about 10,000 terms. So we have to go 10,000 terms to get this within 10 to negative 4 of the actual sum. So as you see, it takes 10,000 terms to get up to 4 decimal places. So that goes extremely slow to 0, right? So we need 10,000 terms to get 4 decimal places. So that's rather slow, but it will go to 0. Right. Now this is a lot more important. Absolute and conditional convergence. Definition. Assume that the series converge. Of course, when we set the series converge, obviously this is converging as n go to infinity or as k go to infinity. So the infinite series in here kind of redundant, because when we say convergent, it will converge at infinity. Then the series converge absolutely. Converges absolutely if the only thing different here is we're going to put the absolute values in it. So pretty much it will be convergent when we put absolute values in it. Otherwise, the series converge. Converges conditionally. Right. On big scheme of thing, just look at the first example. Right. It says that alternating harmonic series converges. The alternating harmonic series is this. This one converges. Now what happens if we put absolute values into it? Now, if we put absolute values, the negative 1 or 1 is still 1, right? So Right. So let me write this out. If we have 1 over 1 minus 1 over 2 plus 1 over 3 minus 1 over 4 plus, if it is like this, it is convergent. Now if we turn all the negative to positive, this will be divergent, because this is a P series and P equal to 1. If P is equal to 1, it is divergent. So that one divergent, this one is convergent. Now when we have this, we say it, so converges conditionally because if we throw in an absolute value, if you throw in absolute values, it will become that series. Which is diverse, which is divergent. Right. So bottom line is, if the series is convergent, and then we put absolute values in it, it is not convergent anymore, then we call that converges conditionally. Now if it is convergent and we put absolute value to it and still convergent, then we say it is convergent absolutely. Meaning absolutely convergent is the convergent with the absolute values. Right. Next theorem, and that is the important part here. So theorem, it says if the series converges absolutely, then it will converge conditionally, or we just say converge, period. So if we have the absolute values and it converges, then without the absolute values, it will be converged as well. It will converge as well. Right. So in the note, what I put was absolute convergence implies convergence. That is, a series converge with absolute values, it will be convergent without it. And that is very important too. if the series diverge, then throw in the absolute values is still diverge. Right. Let's look at a few notes here. First, no such thing as there's no such thing as absolute divergence. Or absolutely divergence. Right. And the second one, the relation to this is called the contrapositive. Remember, convergence, absolute convergence, go to convergence. If we want to go the other way around, it has to be divergence. We have to negate this. For example, let me just write this. It's just logically. P implies Q is equivalent to not Q implies not P. Right. An easy example to this is if I live in Dallas, which implies that I live in Texas. Now, if we want to write that in reverse, I should not say reverse, I call it should be contrapositive. So, I don't live in Texas, which implies that I don't live in Dallas. So those two are equivalent, logically equivalent, and we call that contrapositive. The relation between this. So in this case, I go back to our statement. Absolute convergence implies convergence. Now, if we want to flip that, then we have to negate the convergence to divergence. But we don't have absolute divergence. We have to negate this too. So we just say diverges. Because this is absolute divergence, it's not a thing. So we just say it will diverge with absolute values. Right. So that's a little note behind. Bottom line is, this is what we need. If the series is convergent with an absolute values, it will be convergent. So that's what we need is here. Along with the definition itself. That. Let's look at this example. Example. Determine whether the following series diverges. Converge. Absolutely. Or conditionally. Right. Let's think about this in terms of a graph. Now, if we're talking about the terms, if we have the terms like this, and if we add them, all of them. Now, if instead we have this, instead of just go up and down changing, then which one have more of a chance that approaching to a numbers, right? So we have k, by the way, is k to the 1/2. So let's write that. Right. So, by the way, according to this theory, if it is absolute convergent, it will be convergent. So first thing we do is just put the absolute values in and see if it is convergent or not. Because if it is convergent, that will be absolutely convergent. Don't need to do anything. So first, check for absolute convergence. So we start with the series. And I'm going to put an absolute value to it. When we put an absolute value to it, this term will go away. Because -1 to k plus 1, it could be either -1 or +1. Absolute values of positive or -1 is just 1. Yeah. So we don't have that term anymore. Again, absolute values of -1, I should just say this. -1 raised to k or k plus 1, doesn't matter. Absolute values of that is equal to 1. Right. Now what kind of series is this? By the way, in section on page 86, they list all the series, all the tests for all the series. So that will certainly be handy to have. So this is a P series where P is equal to 1/2. With P equal to 1/2. And 1/2 is less than or equal to 1. So which means it is divergent. So this one fails. So that doesn't work. Now, so with absolute values, it does not converge. How about without absolute value? Right. So without absolute values, what kind of series do we have? Right. Now without absolute values, that's what we have. And of course, because of -1 to k plus 1, this is alternating series. Right, for alternating series, need to check two things. First, by the way, certainly we check two things, yes. But first, for alternating series, just let a sub k be what's left without that -1 raised to k plus 1. So in this case, a sub k is 1 over k to the 1/2. And if we want to, we can say the function equivalent to it is 1 over x to the 1/2. Right. So, first thing we check is a sub k non-increasing. Right. So either we take the function, take derivative, or we just trying to reason without taking derivative. Now we have this. Now the reason is this: if k is getting bigger, the denominator getting smaller. As k getting bigger, 1 over k to the 1/2 getting smaller. Or just write like that. Because if it's getting smaller, that means it is non-increasing. Or because if it's going down, when k getting bigger and bigger number, the whole thing gets smaller and smaller. Therefore, it is decreasing. Which is also non-increasing. So yes, let's check. Of course, we can also take derivative, but right like this is a lot better. And it is better if we kind of understanding how it goes. Bottom increase. If the bottom increase, the whole thing decrease. So the series, I mean the sequence, as k increases, will get smaller and smaller. Okay. It certainly gets smaller and smaller, but does that go to 0? As k goes to infinity. Right, so this also fairly simple. Don't have to do much, just put in infinity. Infinity to the 1/2 or square root of infinity is still infinity. Finite divided by infinity is 0. Yes, so this equal to 0. So that check. since both of them are satisfying, this series converges. However, it is convergence. With absolute values, it is divergent. So in this case, we say it is converges conditionally. Because if we throw in absolute values, it will be divergent. All right. So with absolute values, divergent. Without it, convergent. Therefore, we say it is converges conditionally. It is convergent conditionally. Right. Now, let's further discuss about this. Now, if we're going to write this out, this is the square root. So we start with, when k equal to 1, 1 plus 1 is 2, negative 1 to the second power is 0, is positive. So we have 1 over square root of 1. The next one is negative, square root of 2. Right. So that one is convergent. Because we did check alternating series. Now if we throw in the absolute values, if we throw in absolute values into it, all of this will become positive. And that is divergent. So think about this. Comparing the two series. Comparing the two series, the first one is a lot smaller, right? Because it's negative instead of positive. So instead of adding a number, we subtract, then the result obviously is smaller, right? So because if it's smaller, it is convergent. Now, this one, all of them are positive, so it's going to be bigger than that. It will be divergent. And then you say, but the last term go to smaller and smaller to 0, right? So, and I would agree to that. Of course, when k goes to infinity, the n term will get smaller and smaller, and essentially goes to 0, right? But the idea is it goes to 0, yes, but it does not go to 0 fast enough for it to be convergent. The breakpoint here is where p equal to, this is a p series by the way, when p equal to 1, if it is equal to 1 or below, it will be divergent. If it is bigger than 1, it will be convergent. That is the p series. I should put the bookmark here. So, convergence when p is greater than 1, and divergence when p is less than or equal to 1. That is the p series. So if that one, this series does not converge, because it go to 0 but not fast enough. If we want to go faster, go something like 1 over 1 square, 1 over 2 square, 1 over 3 square, 1 over 4 square, and so on. The bottom go faster to infinity, the whole thing will go faster to 0. In this case, that one is convergent because it go to 0 very fast. So not only we need the term go to 0, but it have to go to 0 fast enough if all of them are positive. If they're alternating, it doesn't matter as long as it is decreasing in magnitude. Right. So just want to add this, kind of get the idea of about the series. Right, so that's the first one. Probably keep that for a moment. Right, 2. How about we have the series this is very important. Right. Yeah, how would we do something like this? So what did we do? So first, check for absolute convergence, meaning put absolute values into it, see what happens. Let's just put absolute values into it. I'm going to put absolute values into it. By the way, k is from 1 to infinity, so k is positive. K squared is positive, so we don't really need the absolute values for k squared. We just need the absolute values for sinc sine of k. Right, now, remember when we do when we have this series, what do we do to test the convergence or divergence? There are a couple ways to do it, but the elegant way is that absolute values of sine k, we always have this, right? Usually when we have sine or cosine, this is between -1 and 1. So the square theorem usually when sine, cosine, we use the square theorem. Now if we put absolute values into it, so sine of k, put absolute values, of course it's less than or equal to 1. Right? And then after that, why don't we divide by k squared on both sides? So we have sine k divided by k squared will be less than or equal to because of that. Now, what happened to the series? So what kind of series is this? By the way, this one we just talked about. That one, right? And this is a P series where P equal to 2. P equal to 2, which is greater than 1. And this is convergent. If P is bigger than 1, it is convergent. Now, if this is convergent, anything less than convergence is also convergence. And that is direct comparison test. Mathematically, this is writing like this is not really correct, but the idea is right. It's easy to understand that way. So if that is convergent, anything less than that is convergent. So the series is convergent as well. And it is converges with the absolute values, therefore it is converges absolutely. Because we have the absolute values, right? Now we have the theorem that says if it is convergent with absolute values, it will be convergent without it. That is the theorem we have, right? If a series is convergent with absolute values, it will be convergent without it. So this one converges absolutely, meaning without absolute values, it is also convergent. So that's why we say this one convergent absolutely. Now think about it. Say something easier like this. Let's say all of them are positive, right? And it is convergent, so this is equal to some numbers, right? Think about that. Now, instead of that series, what I do is let's change one of the term to negative. Let's change this next one negative as well. So remember, this one is convergent, so that add up equal to some numbers already. Now, instead, we throw in some negative into it, meaning we're going to have a number that even less than the number that we have earlier. So let's this equal to L, some number, some limit. If instead of a positive we have a negative, we will have a number that is even smaller than L. Of course, that's going to be convergent as well. So if it is convergent absolutely, meaning if it is convergent with absolute values, it will be convergent without the absolute values. So that's why either this one we use the Swiss theorem, but Swiss theorem only can test for a term. This one we can test for the whole sequence. Right? So let's take a 5-minute break. When we come back, we go to the next section. We skip this one because that actually we're going to do that one too, but I take 5-minute break. We continue at 9:12. By the way, I sent you an email last night about pretty much what we're going to do for the remaining of the class, about homework, tests, finals, and pretty much anything. If you have any question about that, please send me an email or you can ask now. Right. We continue. Right. Of course, first put absolute values into it, see what happens. By the way, normally we do not do this. If the question just asks for convergent or divergent, we don't just put absolute values into it on all of them. So when we put in the absolute values, at the bottom doesn't matter. The k doesn't matter either. Only turn the -1 to infinity. I mean -1 to the k power. It's the only thing that matters. Is the -1 to the k power. And absolute values of -1 or 1 doesn't matter, it's still just 1. Now, what is the divergent and convergent of this series? Alright. When we go to section 10.8, we'll discuss which one do we test first, but I'm telling you right now, the first one that we test is always what happened at when k go to infinity. And of course, we take the limit of this many times. We take the highest degree top and bottom, because that when k goes to infinity. Plus 1 here doesn't do much. Infinity plus 1 is still infinity. Right? So what does that tell us? Now, since that does not go to 0 as k go to infinity, if we're just adding a bunch of numbers and the last number does not go to 0, that means it will change constantly, right? If we just add, think about this. Something like this, when we just keep adding, the number gets smaller and smaller. Eventually, we're approaching to a number. Now, instead of adding this, we're adding this instead. The number just keep getting bigger and bigger. That's not really important though. What's important is the last number is not going to be 0. So just keep adding something new to it, because you just keep adding something that is not 0 into it. That will change constantly, and because of that, that is divergence. And this is what we call the Divergent Test. If the n terms, if the term when k go to infinity does not go to 0, the sum will just changing, and because of that, it will not be convergent. If it go to 0, well, we don't know. It is inconclusive. Right. Next, just take away the absolute values. or when we don't have the absolute values. And of course, when we have this device, this is the alternating series. So we will check AK will be K over K plus 1. And we check two boxes. Doesn't matter for the first one. With the second box, where K goes to infinity of K plus 1. For alternating series, the last term go to 0. That one fails. So this one divergence as well. So it is divergent with absolute values, divergent without absolute values. Therefore, it is just divergence. So this one is divergent. Right. So put the absolute values into it. If it is convergent, it will be convergent absolutely, and then we don't need to do anything further. If it is convergent with absolute values, it will be convergent without it. If it is convergent without the absolute value only, that is called conditionally convergent. Right. The ratio test and the root test. The ratio test, by the way, it is one of the go-to tests. Most of the engineering, I should say engineering usually use the ratio test. Of course, this will be the first test that we're going to test, is the divergent test. After that, the ratio test is the reference. Right. Section 10.7. The ratio test and the root test. Right. Let's look at the theorem. Let the series be an infinite series. And let R, this is not a ratio or anything, by the way, it is a ratio, but not like the ratio in the geometric series. So R is the ratio as K goes to infinity. What we do is we're going to take the next term divided by this term with absolute values. Then there will be three scenarios. First, if the ratio is less than 1, the series convergent. Is convergent. Because we put the absolute values into it, it will be convergent absolutely. If it is convergent, absolutely it will be convergent. Two. If the ratio is bigger than 1, that also including the case when it is equal to infinity. The series is divergent. And if it is equal to 0, the test is inconclusive. So as mentioned before, this will be the second test that we're going to take. The first one is what happens as k go to infinity. That is the divergent test. That is the first test we use. The second one will go to be this one. By the way, you might think that, you might see that this is the ratio. The limit comparison test is also a ratio, right? Here. Sorry. So limit comparison test, it is also a ratio. However, the difference between the ratio on the limit comparison test and this ratio is that both of the terms come from the same series. As the limit comparison test, they come from two series, a sub k and b sub k. So that's the difference between the two. Right. Go to the note before we do some example. We use the ratio test a lot. It's helpful for when we have k to the k power. What's that? K factorial or a to the k. B. Example. Use the ratio test to determine whether the series converge. Right. Let's look at first example. Ten to the k over k factorial. Right. So first, in order to write the ratio, we have to know what is a sub k. So a sub k is the term in the series. So first, let's h of k be in that. Then we will use the ratio test. R equal to limit at k goes to infinity the next term divided by this term. So the ratio of the next term divided by this term, put absolute values. Right. When ka of k plus 1, pretty much instead of k, we have k plus 1. So put k plus 1 here, here, and there. So we have 10 of k plus 1 instead of k, and k plus 1 factorial. And then the bottom h of k will be just that. Before we go any further, what do we mean when we define what is factorial? Our factorial of a number is the product from that number back to 1. So 5 factorial, just say 4 factorial is 4 times 3 times 2 times 1 will be 24. So that is factorial. Right. Now first we're dividing though. Dividing is multiply reciprocal. Multiply the reciprocal, k factorial 10 to the k. Right. At this point we can drop the absolute value because all of them are positive, but I just keep it. Now 10 of k plus 1 is going to be 10 to the k times 10 to the first. Because when multiplied two things with the same basis, we combine the exponent. Right. K plus 1 factorial is k plus 1 factorial is k plus 1 times k minus 1 all the way back to 2 and 1. Right? Start from that number, multiply backward until 1. Now, the k back to 1 is k factorial. So, the k factorial is equal to k plus 1 times k factorial. Yeah, k plus 1, and from k minus 1 all the way to 1, we can replace that by k factorial. And then we have k factorial over 10 to the k. Right? And it will just grows out. Ten to the k, 10 to the k. So we cross those out. We left with 10 over k plus 1. Since k is positive, because k go to infinity, we don't really need an absolute values. Right. We have 10, k goes to infinity, finite over infinity is equal to 0. So according to this test, this is less than 1. So we say this one convergent, absolutely, or just convergent. Right. So it's not that bad. Usually when we have this scenarios, use the ratio test. And the application is fairly simple. The next term divided by this one, and then there should be a lot to cancel out. And if it is less than 1, it is convergent. Two. How about we have k equal to 1, to infinity, k to the k power, k factorial. Right. So first of all, obviously we're going to let a of k equal to that. And then we'll take the ratio with the limit as k goes to infinity. Right? Right. H of k plus 1, that is where we'll replace k by k plus 1. So we have k plus 1 to the k plus 1 over k plus 1. Sorry. Should write k plus 1 to k plus 1 over k plus 1 factorial, because that is the ratio of the ratios. Right. Let's start from right. Let's h of k equal to k to the k over k factorial. Right. Then the ratio of consecutive terms. The next term divided by this term. Right. When k plus 1 instead of k, substitute into that. K plus 1 factorial at the bottom. K plus 1 to k plus 1. Right, so that's what we have when k goes, when we have k plus 1 instead of k. Right, and at the bottom, k to the k, and then k factorial. Okay, divide fraction is multiplied reciprocal. Reciprocal. Factorial on top, k to the k at the bottom. Right, so we flipped the second ratio, second fraction. Right, now first the k plus 1 to the k plus 1, it's going to be k plus 1 to the k times k plus 1 to the first. That gives us, when we multiply, combine the power, times k factorial. The bottom, k plus 1 factorial is k plus 1. Talk about this many times. K plus 1 factorial is k plus 1 and then times k minus 1 on the way back to 1, which is k factorial. We see a lot if we have factorial. That's what we do. That equal to that. And then k to the k. Right, so what can we simplify in here? Let's see, the factorial cancel out. And we also have the k plus 1 here cancel out as well. So we end up with this. By the way, we don't need the absolute values now because all of them are positive. Now, since both of them under the power of k, let's move that inside. and write this instead. By the way, I'm sure you see this one before. You think what's that equal to? If we go way back, probably the second day. We've seen this one before, right? This is back in section 7.6. By the way, that is the definition of E, which is 2.71828. That's a natural base. Right, so that's equal to E. But in terms of ratio test, what did that tell us? Right, ratio test, bigger than 1, divergent. So this one bigger than 1 will be divergent. Right, so now actually if we go way back to this one, the list, the ranking, we have the factorial is less than n to the n. By the way, I think that calls superpower. I mean n to the n. Right, so that is the biggest one. So this one will go to infinity faster than everything else on the list. Certainly faster than factorial. Now, if the top go to infinity faster than the bottom, if that is the case, the top go to infinity faster than the bottom, meaning that the whole thing will go to infinity, right? Because the raised on the top go to infinity, infinity divided by something that's less than that, significantly. So that would be infinity. So since the n term does not go to 0, this one is divergent. By the way, another way to think about this is where we say k to the k power, for example. K to the k. Example, if we have 5 to the 5 power, meaning that we have 5 times 5 times 5, 5 times, right? Now if we have k factorial, for example, 5 factorial, we have 5 times 4 times 3 times 2 times 1. Because factorial, the number getting smaller and smaller when we multiply in compared to the superpower of all of the numbers are the same. We have the same number of factors. There are 5 of 5 and then 5, 4, 3, 2, 1. Obviously the 5 to the 5 is a lot bigger than this. If the numbers do not drop, we have a bunch of those factors. That will be a lot bigger than the factorial, right? So if the top is bigger than the bottom, the whole thing will not go to 0, and because of that, right? So only 5 on the top, and then 5, 4, 3, 2, 1. So because of that, if this pattern continue, the top is going to be a lot bigger than the bottom. That does not go to 0. Therefore, it is divergent. And so that's why this ranking is very useful. If we have that one divided by something on the left, that will be divergent. On the other way, if we have a term on the left divided by the term on the right, it will be convergent. Right. Like I said, the ratio test is one of the more versatile tests. That, like I said, will be the second test that I'm going to use right after the divergent test. But we'll talk more about the strategies in the next section. Now we go to the root test. In contrast, the root test is probably the last test that actually the second to last test that I'm going to use. So the ratio test is a lot more useful than the root test. The root test is very situational. Let the sum be an infinite series. Right, we call that rho equal to the limit so we're going to take the k root of the h of k. Now the conditions are similar to the ratio test though. If that less than 1, right. By the way, the row is not a p. P usually we write like that, and the row is like that. Row, the Greek letter. So the series, if the row less than 1, the series converges. Absolutely. Therefore, it is convergent. Once again, if it is convergent with the absolute values, it will be convergent without it. Now, if p is greater than 1, it's not p, sorry. If rho is greater than 1, the series diverges. Of course, this also including infinity. Three. If the ratio equal to 1, it's also inconclusive. Yeah. So in terms of the ratio test, kind of the same thing here. Like I said, it's very situational. We only use that when we have the k power, because the root cancel the power. B, not. The root test is helpful. When we have something to the k power, the whole term raised to the k power. For example, something like this. Example. Use the root test to determine if the following series converge. So let's look at the problems. So we have this problem. Obviously, this one makes perfect sense to use the ratio test because we have the k power. If we take the ratio, the power cancel out. That works perfectly, right? Right. Now this, even though we have the power k here, and certainly the root test can be used here. However, for something like this, I'm just going to use the ratio test. Like I said, unless I have the whole thing raised to the k power, use the ratio test. Use the root test. If I don't have that, try something else. The root test is very situational. It's only for something raised to the k power. Right, so determine if use the root test to determine if the following series converges. And this is the series. Not that. This. Right. So like that. Right. So first of all, of course, h of k is the whole thing. Right. So let that. Now, obviously, when we have the whole thing raised to the k power, use the ratio test. So we're going to take. Sorry. Let's do that again. If we have the whole thing raised to the k power, use the root test. Because the root test will cancel the power here nicely. So we can take the root of h of k. So with the power, the root will cancel the power. And the reason we can do that because this is positive, so that will cancel out nicely. Anyway, we don't have to worry about imaginary. Right, the power and root cancel out. We just have four k squared minus 3 and 7k squared plus 6. Now when k go to infinity, 4k squared is a lot bigger than 3 and 7k squared is a lot bigger than 6. The reason, by the way, we put 4 instead of 2, because if we have 2k squared, when k go to 1, 2 minus 3 is negative. So the problem is actually they have 4k squared for a reason. It could be 5. It's perfectly fine. But if this is 2, the term is negative. So technically they works out for a reason. Anyway, that term is a lot bigger than negative 3, and 7k squared is a lot bigger than 6. Of course, we use the ranking like this one. Any power is bigger than a constant. Do we just have 4k squared for 7k squared? Take the highest term on the top, divide by the highest term at the bottom. The k squared cancel out. Just have 4 over 7. And there's no k to substitute in, so that will be the limit. And that one is less than 1. If the ratio, if the root is less than 1, it will be convergent, absolutely. In terms of the ratio and the root test, the criteria are very similar to each other. So the series converges, absolutely. Yeah. By the way, in the ratio test, we should have the term inside being positive. If it's negative, that is the problem. Right. Just quickly go to the next test. I'm not going to do the example that we have there. I'm making something else. So how about this one? Yeah, do that instead of this one. Right. So just jump right into it. And then take the row equal to the root. Because we have the power there, right? So the root cancel the power. Right. So for this one, if we put infinity in for k, finite divided by infinity, that go to 0. So this equal to 1. So what does it says if rho equal to 1? When rho equal to 1, the test is inconclusive. Oh, it doesn't help. Right. Right. Now, however, if we just take the limit of the n term to the k term, and that is equal to e, which is not equal to 0, and this is divergent by divergent test. Right, so as mentioned before, usually when we have the k power, we use the root test. Even then, that could be inconclusive. And this is the divergent test. Divergent test is if the n term or if the k term does not go to 0. So if the last one is not going to go to 0, so the sum will be constantly changing, because you just add a number to it, and that number is not going to be 0, so that will changing every time. Therefore, that is divergent. Because if we just adding a number that is not equal to 0 to it, it will change. If we keep doing that, it will still changing, and therefore it cannot be convergent. It has to be divergent. Right. So with that, we go to section 10.8. On 10.8, we just summarize all the tests that we have, and which one do we use. By the way, I'm not going to draw the whole table again because that takes too much time. By the way, this is page number 86 on the note. Like I said, it will be very useful when you take the test and have that with you. Right, let's take 5-minute break. When we come back, we'll discuss the strategies of which one do we use to test what series. Right, we continue at 10:10. Don't worry, but it's still on. I just change this real quick. That's good. Right. So this section 10.8 we discuss on the test for the convergence or divergence of a series. We will not go over all the examples here. Convergence. Test. Right. First summary. Right. Like I said, I'm not going to write the whole thing here again, but that table that's all of it. Like I said, if I write that, it's not going to be as nice as we have there. So I just say C note on page 86. What we do instead of writing the strategy. By the way, let's just a quick overview. So this, we have 9 tests here. 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 tests here. Like I said, the first test we're going to use, I would refer as the first one we check is what happened if the nth term goes to infinity. So we take the limit of the nth term go to infinity. That's the first thing we do. So the nth term test or the divergent test, k-term test, is the first thing we do. Take the limit of a single term when it goes to infinity. That's the first thing. Right. After that, comparison test and limit comparison test. Usually, if it works for comparison test, it works for the limit comparison test as well. So after those 2 tests, the limit comparison test is a lot easier to use, even though it's not as elegant as the comparison test, but it's easy to use. And so limit comparison test is preferable. So I could completely take this comparison test out of it. So number 1 option, divergent test, and I just going to take the comparison test out of the way, because sometimes coming up with the second series is kind of difficult. Right. So, and the last we're going to use is the integral test, simply because it requires it to be continuous, positive, and decreasing. So there we have a lot of things that we have to check, and also the integral sometimes, or I should say most of the time, is a lot more difficult than to do than using all other things. So the first one, divergent test. The last is the integral test. The second to last is the root test, because that kind of situational. We have to have something to the k power to use the root test. So we cover divergent test, integral test, and root test. Right. So the second test that I would use is the ratio test, because it's very versatile, can use a lot of different things. So the ratio test. And the next one is either alternating series or limit comparison, because those are very versatile. The alternating series, though, is easy to use when we have -1 to the k power. So that's probably the number 3 that I'm going to use. Number 4 is the limit comparison test. Usually we compare to the geometric series and the p series. Right. So I think I cover everything. Of course, what we don't have here is the telescoping series. We could have that as well. Right. So let's just summarize what I just said. B. Strategies. Right. This is, once again, it's just my reference. You sometimes if we look at the problem and you can just go straight to, and you know directly what method you use, then you don't have to go through all of this. Again, just what I would prefer to do when approaching the problem. So first thing, I use the lowercase Roman numeral. So that is number 1, is the divergent test. Divergent test here. So what we do is we will take the limits of h of k as k go to infinity. If this is equal to 0, inconclusive. If it is something else, it is divergent. Right, so the first thing I do is the divergent test. Second is the ratio test. like I said, just my preference. It could be the limit comparison test. Usually those two. Ratio test or limit comparison test, like 2 or 3 kind of interchangeable. Right. Let's use the ratio test. Actually, yeah, the reason I go with the ratio test because that is most of the engineering. The first thing they, after that they will go straight to the ratio test, more applicable. But actually, I would go with the limit comparison test. So let's ignore that. Sorry about that. So limit comparison test. By the way, at the end of the semester, definitely I will ask you about the note for this part. So make sure you have it. Right, limit comparison test. The most importantly in here, the most important things here is what do we compare to? So in order to use the comparison test, we need this. I will write the ranking again. Yeah, this is the useful. So we're going to use this. Next, what do compare to? So most of the time when we have the limit comparison test, for example, when we approach a problem like this, we use this to reduce and just ignore the term that is less than significant, less than I mean ignore all the term on the left of it, right? So what do we compare to? Usually we will compare to we ignore using that ranking. So just write. So we use this ranking to eliminate some term that is significant less than the others. For example, if it is k squared plus 1 as the ratio like this, I'm just going to take k squared. The plus 1 doesn't do much. Neglectable. Right. And what do we actually compare to? And we usually compare to when we eliminate this term, what we have is usually compared to P series. That is the P series. And if P greater than 1, convergent. Less than or equal to 1, divergence. So we usually compare to the P series or a geometric series. Geometric series is a constant, and then R to the K. Right. This one, the sum doesn't matter. Actually, this also doesn't matter, but we may have the ratio absolute value. If it is less than 1, convergent. Greater than or equal to 1, divergent. So usually when we eliminate the terms that are negligible, we will end up with this 2 series. Right, so that is number 2, limit comparison test. Number 3 is the ratio test. And we did write out when do we have to use the ratio test. Usually when we have k to the k factorial, k to the n, or n to the k, constant rule of k. So let me just write down that part. Ratio test helpful for these scenarios. Because A is a constant, K is the index. Right. What is actually the ratio test? R will be the limit. AK plus K over AK. And again, we have 3 scenarios. If this is or less than 1, convergent. Equal to 1, inconclusive. And bigger than 1, including infinity. That is where it is divergent. Right, next. Alternating series test. Now, out of all of those tests, this one is usually the first when we see the problem, it's very distinctive. So we know, usually we know right away that we use alternating series test, because usually when we have -1 to the k or -1 to k plus 1 or something, that -1 raised to some power, and then finally the application is when we have -1 to the k power or plus 1, doesn't really matter, a sub k. The a sub k here is positive. So two things we need to check for. First, by the way, a of k is non-increasing, and the second one, does it go to 0? So those are what we need to check for. Right. So how many we have so far? 4 of them, right? And then these 2 more, so it'll be 6, and with a total of 9. So we have 9 tests. We have 6 already. And like I said, I'm going to exclude this one, because the comparison test, you can just go ahead and use the limit comparison test. Even though it's not as elegant, it certainly works. So we ignore that. We have 8 left. So just the root test, and the last one will be the integral test. Root test. Now what we have for the root test? By the way, when we write like this, the a sub k should be positive. Otherwise, oh, never mind. We put absolute values there, right? Right. Yeah, that's what I was worried about. If we put absolute values here, then there's no problem at all, because that guaranteed to be. So negative is okay. Don't worry about it. Yeah, this is correct. Put absolute values into it. I forgot to write it earlier. Yeah. Right. So it's fine then. And when we use that, usually where they are something to the k power. Right, next we're going to let rho equal to limit at k go to infinity the k root of a sub k, just to guarantee that's positive. Put absolute values. Now it certainly works. Right. 3 cases. When it's less than 1, it is convergent. Absolutely. Equal to 1, inconclusive. and greater than 1, including infinity, is divergent. And finally, the last one I would use is the integral test. Right, integral test. There's a lot. First, we're going to have f of x or f of k equal to h of k, and require three things: positive, continuous, and decreasing. Continuous, positive, and decreasing. So in that case, we will integrate instead. Find the sum. Right. So this is an improper fraction. If this one is convergent, then the series is also convergent. If this one is equal to infinity or does not exist, or if the improper integral is divergent, then the series is also divergent. Just one little thing though. The root test and the ratio test, when it is convergent, because we throw in the absolute values, this will be convergent. From the ratio test, convergent absolutely. And the root test also convergent absolutely. So because we throw in the absolute values, that's why. Right. So that's all we have. I'm not sure it will fit into one screen. Oh. Yeah, that works. So those are all the tests we have. And like I said, it is just my reference. Right. That summary is pretty much the whole chapter. Start from 10.3. So when we test a series, there's a lot of things we can do. If you can see right away which method we're using right away, that will be nice. But if not, at least we have a list of that we're going to check as we go along. Right? I think this is actually almost as good as the table you have over there. Let's zoom back in. Right. Now just go through a bunch of examples. We might not go all the examples here, but at least we have to do quite a few of them. exercise. And on all of this, we just determine if the series converge or diverge. Like I said, the direct comparison test, actually this one is the more elegant, a lot more elegant than the limit comparison test. However, if you can use the comparison test, then you can do the limit comparison test as well. It is elegant. Usually the proof is very short. However, like I said, it's more versatile. We can use a lot more application if we use the limit comparison test. Right. So let's look at the first example. We have the series k equal to 1 to infinity k over ln of k plus 1. Right. So, by the way, by the limit comparison test, there's a reason I put this on number 2, where we use the limit comparison test and refer to the ranking here. Ln of k obviously is going to be bigger than a constant 1, so we just ignore it and then just do that. Right. Actually, there should be a little more than on a limit comparison test. So on a limit comparison test, actually we have to write the comparison, the ratio. So that means this. So for A case, what we're going to do is we'll take the limit. K go to infinity, bk or ak over bk, doesn't matter which one divided by which. Let a of k divide by b of k. And if this one is less than infinity, it's convergent. I mean, it's not convergent. Sorry. Right. If that one less than 0, infinity or greater than equal to 0, then AK and BK behave the same. Meaning both of them converge or both of them diverge. Right. Yeah. Please add that to the note. Yeah. Right. We referred back to that many times. Right. So the first one we always check is what is the limit of that term when it goes to infinity. So what happens if k goes to infinity? What is the limit of that? So when we're taking the limit, refer to the ranking, we can knock off a bunch of terms. That is not as big as it. So ln bigger than k, so just ignore it. I just write here because ln of k is significantly bigger than 1, go to infinity faster than 1. Of course, 1 does not go to infinity at all. 1 stay 1. Right, I'll take the limit, put in infinity. Infinity over ln infinity. Ln infinity is also infinity. So this one is indeterminate. So in that case, what we use is the Harmonic rule. Taking derivative of the top, derivative of k is 1. Derivative of ln is 1 over k. Divide fraction is multiply reciprocal. Want to flip. So we just have that. Now put infinity into k. Obviously this equal to infinity. So what does that tell us? So what we use is the divergent test. First thing, divergent test, if it is equal to 0, inconclusive. If it is something else, divergent. And so this is something else. It's not equal to 0. So this is divergent by divergent test. That's usually the first test that we will take. Right? Right. Next we have the series right. So that, what do we do? Divergent test. Let's see what happened when k go to infinity. That's usually the first thing we do. So we take the limit of that term. That's why I said always have this in handy, because once again the power is going to be bigger than constant. We take the highest power, not just the highest power, whatever bigger, whatever on the right, and ignore everything on the left of it. So take the highest power. So first thing we do, always take the limit, see what happened. Because if it is divergent, then we don't have to do anything else after that. Right, k and k cancel out. And now what we have is 5 and then over infinity for k, finite over infinity, that equal to 0. Equal to 0 is inconclusive by divergent test. Right. By the way, we're not stop there. If it's inconclusive, we should try something else. Right. So that doesn't work for divergent test. That's alright. Go to the next one. So what is the next one? Right. Limit comparison test. This was section 10.3, so a while back. So we're still on this one. So what do we compare to? We can compare to the series without it. But for the limit comparison test, first, let AK be that term. And then we find BK. To find BK, refer to this list again. Just take the term with the highest space, which is the term that on the right most out of all of them. So a k square instead of k. So that will be b sub k. Choose b sub k equal to again check the one on the right, ignore the term on the left of it. We can even ignore the constant if you want to. Yeah, so you choose 1 over k. Even we can ignore the constant. Once again, for the limit comparison test, refer to this one and then take the one with the rightmost. If usually their ratio, take the one on the right, ignore the term on the left of it in this ranking. Right. And then next we will take the limit of AK over BK. As k goes to infinity. Notice that this is not the ratio test. Ratio test is two terms come from the same series, come from the same sequence. This completed two different ones. One is given, one is chosen. Right, so 5k over k squared plus 2 and b sub k 5 over k. Divide fraction is multiply reciprocal. Flip this. Equal to limit don't know why I put the 2 here, right? For no reason. Right. Cancel the 5. K square over k square plus 2. So we find this limit. And of course, when we find the limit, take the highest power terms, ignore what's on the left of it. That's when we take limit though. So this is just equal to 1. Right, I'll go back to limit comparison test. What do we have? First, we have to take the ratio and make sure it's between 0 and infinity, meaning that it's going to be finite. So what we have is, it is 1, therefore it is a sub k, b sub k. It is less than infinity, 1 is less than infinity, and greater than or equal to 0. So which means AK and BK behave the same. The series AK and the series BK behave the same. And then the question is, what is the series BK? Is that convergent or divergence? Right, B sub k. Take out the 5. What we have here is a harmonic series, or more general, a P series. We see a lot of this, right? So this is P series, P equal to 1, which is divergent. So that is usually when we do the limit comparison test, usually we compare to a P series. If P is greater than 1, convergent, less than or equal to 1, divergence, or the geometric series. So usually when we compare to those two series. No, it does not cancel from the beginning because of the plus. If all of them are multiplied, we can cancel. Not from the beginning. We cannot just cancel the k and k here. We cannot do that. We can do it when we have 5k over k squared. Then we can simplify. Yeah. With the plus 2, we cannot just simplify the k. Right. Yeah. So that's why usually we refer to this. That's simplifying a lot. And then with that, we can just cancel out like this. Right. So now, so B sub k is divergent, and they behave the same. So A sub k is divergent as well. So this divergent also, because they behave the same. One of them is divergent, the other one is divergent as well. So usually the reason that the limit comparison test is very useful, because the problems usually are complicated like this or even like that. All we do is using the ranking here, take the highest terms, and then we just compare to what's left here. If that series is convergent, the original series is also convergent. If that series divergent, the original series is also divergent. So that's why it's very versatile. So what we do here is the limit comparison test. Divergent test doesn't work because that's inconclusive. So we'll go to the limit comparison test. By the way, I think I answered your question about the k and k here do not cancel, right? Right. I didn't realize it's 11 o'clock already, so then we have to stop here. We pick it up on Wednesday, where we continue on this doable. Alright, thanks. Right. Yeah. So the ranking is very handy. So make sure you have this when you take the test. We stop at this example. We continue from here on Wednesday. By the way, a quick overview. Chapter 11, even though we have the note, but I will not go over everything on chapter 11. We go over the important things, because honestly, like I said, if you take in count 2 and the power series or this kind of things is the first thing that you forget. So because of that, I will focus on something that is extremely important that you really need. Because I cannot focus on everything, only focus on a few things. So chapter 11, we focus only on the important parts, so we will not take a lot of time. So we write on the schedule though. And chapter 12, also I focus on the important things. We cannot focus on everything though. Right, before I end the stream, do you have any question? Once again, I sent you an email last night. We'll have that has all the important details about the class, the final exam, the homework, and all other things. If you have any question, please send me an email. Right. If not, I'm going to end the stream here. By the way, today I connect using the cable, not the Wi-Fi. So it seems a lot smoother. So I don't think there's a lag during this stream. Oh yes. Yes, the reason that I write everything out rather than write directly on the note, because at the beginning of class when I do the survey, some of you indicate that you don't want to bring them out. So that's why I write everything out. No, the note cannot be the picture of the video. You actually have to write them out. Yes, the note have to be handwritten note. You have to write them. You cannot just take the picture from the video. Yes, I'll give you before the final exam. I will send you the list of the things that I ask you to be that you need to worry about. Yes, of course, the notes are from the video, of course. Yeah. Yes, this comes from the video. Yeah, that's what I mean. It is not like that I ask you to do this to make you watch the video, or I just want to improve my YouTube channel, but because I think it's important that you need to know. Besides, at the beginning, this class is the lecture class, so I just want to keep that part of the class. So that's why I make that participation into like 10% of the class. Right. Should you have any other question? Right. Yes, it goes without saying, because I cannot really enforce a closed book, closed note. So on the test, you can use calculator TI-84, and on the note, really, because you're taking the test on my MATLAB, I cannot really check what you use and what you're not using. But what I ask you not to do is, you cannot look up the answer on the internet, and you cannot ask anybody else. So it's just you and the note and the calculator. If you can use those three things, it's fine. Once again, it's just you, the note, and the calculator. Yeah. So don't look up the answer on the internet, and don't ask anybody else. That don't ask. Besides, that also justify that count 2, there are a lot of different things, a lot of little things. So I think it is fair that you can use the note. Right. Any other question? Right. If you have other questions, please send an email. Send me an email. Other than that, of course, you can always asking anything during the video on YouTube here. Right. If not, I'm going to end the stream here. Have a nice day.